Now we look at line integrals, specifically line integrals with respect to arc length, or line integrals of scalar valued functions. Should warn you there's another type of line integral, common type, that's a line integral of a vector field along a curve through a vector field, and we'll consider those much later. All right, so for this type of line integral, we start off with a parameterized curve. We'll say that C is our curve, parameterized by r of t with domain interval AB. And we have the line integral, specifically the line integral of f with respect to arc length along the curve C. Then we define that to be as we do most integrals, the limit of a sum. So we start off with a partition of our domain for t, partition a to b, and then we're going to plug those partition points into our parameterization. That gives us a point along our curve. We take that point along our curve, and these points along the curve we plug into our function f. That gives us some scalar value. And then we're going to multiply that by a chunk of arc length. So we're taking points along our curve and multiplying them by a chunk of arc length, summing that up and taking a limit. And so that maybe doesn't help right now with a good understanding of what this is doing, but we'll come back to that later. Now, that's the first problem is, what does this mean? Well, and again, we'll come back to that. The second thing is, how do you actually compute this thing, right? Because this is obviously not the way we want to go about computing things. So we want to somehow relate it to an older type of integral that we have an easier time computing somewhere where we can use the fundamental theorem of calculus. So let's make an assumption that r of t is smooth, and that the function f is continuous. Okay, so if we choose a smooth parameterization and a continuous function, then this integral will always exist, and in fact we can compute it as follows. We're going to take our line integral and plug our parameterization in. So what does our parameterization say to do? It says to integrate from a to b, right? That's because that's the domain for t. We're turning this abstract line integral into a regular old definite integral with respect to t. Okay, how about f? Well, we want to plug points in our curve along into f. So, oops, let me make my eraser size bigger for future. All right. So we're going to plug points in our curve into f, and then what's ds? Well, ds represents a chunk of arc length. And so let me remind you, the way that the arc length function is defined, we had that the derivative of the arc length function was the same thing as the length of the derivative of our parameterization. In particular, then, we could write down kind of formally that ds should be the length of the derivative times dt, and this we'll call the arc length element. Okay, so anyway, we plug in length of r prime of t dt for ds. Now there's a couple of things I want to note before moving along. One is a simple interpretation. If we have a simple interpretation if our function f is 1. Notice that if we take the integral of 1 ds, that's the same thing as the integral from a to b of the length of r prime of t dt, and that is nothing more than the arc length of our curve C. Okay, so already we can see that the line integrals with respect to arc length are generalizing the computation of computing arc length. All right, next thing I wanted to point out is that for a smooth curve, if we reparameterize, so we have more than one parameterization, the line integral itself is only going to change by essentially a u substitution, and without going through the details of this, just say, long story short, this guy is independent of parameterization for C. So if you parameterize C in any way you want, any smooth parameterization, then this will give you the same answer. In fact, it's not just independent parameterization, but also of orientation. So it doesn't matter whether you're traveling along your curve one way or another. Either if you parameterize it going either way, this is going to give you the same answer. By the way, that won't be true of the other type of line integral that we study in the future. A third note is I wanted to point out this notion of curve arithmetic. Okay. If you have a curve, let's say C1, and you have another curve, C2, if you travel along curve 1 and then along curve 2, we call that totality of that the curve C1 plus C2. Okay? So you just run one curve after the other. By the way, if you have an oriented curve, say C, then you go ahead and let's say that you reverse the direction on your curve, you get a curve negative C. So we can actually write down expressions like 3C1 minus 2C2, and what that would mean is to run along curve C1 3 times and run backwards along curve C2 twice. The curves don't have to actually start and end in proper places, like adjoining places for us to define this. Anyway, the reason I bring this up is if you are asked to compute a line integral along C1 plus C2, because of the way this is defined, this is the same thing as integrating along C1 and then integrating along the curve C2. So there's a kind of almost like linearity of the argument there. More generally, you could write down things like this, right? If we took the line integral along 3C1 plus 2C2, it's the same thing as 3 times the line integral along C1 plus 2 times the line integral along C2. Okay, so just a little note about curve arithmetic. And so, in particular, if you come back up, we were assuming that we had a smooth curve. If instead we have a piecewise smooth curve, well, we could just integrate along every smooth piece and add up the results. And so now we know how to deal with piecewise smooth curves. Let's go ahead and look at an example. So let's see how to actually compute this. And we'll circle back to the question of interpretation after this. All right, so let's say that we have a curve. Again, often we're given descriptions of curves and we have to come up with a parameterization. This curve, we're actually just handed a parameterization. Okay, notice that that's a circular helix. And let's say our domain is negative pi to 3 pi. Okay, so step 1, if we're asked to compute a line integral, usually it's coming up with a parameterization, especially if we're not handed one. So let's go ahead and compute this integral. The integral along our curve C of x squared plus y squared z ds. Okay. So step 1, we have to parameterize our curve. Check. Okay, that was given to us. Step 2, we need to compute ds. That's an unknown to us at the moment. So remember that ds is the length of r prime dt. So we're going to take the derivative. That's minus 2 sine t, 2 cosine t, 1, and take its length. So we get the square root of 4 sine squared plus 4 cosine squared plus 1. Now remember the Pythagorean theorem that tells us that sine squared plus cosine squared is 1, so that we're left with just the square root of 4 plus 1, which is the same thing as the square root of 5. All right, so now we've computed the length of our derivative. It's time now to plug stuff in. So let's kind of highlight what we have to plug in. We need x. Well, this is x right here. We need to plug in y. Well, this is y right here. And we need to plug in z, and there's z right there. Okay, and then we'll also need to plug in ds, and we've calculated that over here. Okay, so there's our, we've got everything set up. All right, let's go ahead and take care of this. So we have the integral. Okay, we're turning this into a regular old regular old single integral. The integral from negative pi to 3 pi. That's our domain for t, so that's where we integrate. And then we need to plug in x is 2 cosine of t, so we have x squared. And then y is 2 sine of t. We need that squared, so there's y squared. And then this is times z. Oops, but I need to plug in z. Pay attention to what I'm doing. So z is the same thing as t. And ds is square root of 5 dt. So again, we'll make these colors match up. So we have x was 2 cosine t, x squared. Here's x quantity squared. And then y was 2 sine t. We have y squared, so here's y squared right there. And then z is t. There's our z, replaced by t. And then finally, we had our ds, which we calculated to be square root of 5 dt. There it is, right there. All right, now it's just a matter of cleaning things up and calculating. So this is the integral from negative pi to 3 pi. Notice that we have a cosine squared plus sine squared, which is 1. So the first part's just collapsed down to 2 squared, or 4. We have t square root of 5 dt. Right, again, so we'll get a nice clean integral here. The integral of 4t would be 2t squared. So we have 2 square root of 5 t squared, evaluated at 3 pi and negative pi. If you plug in the upper bound, 3 pi squared is 9 pi squared, and so we have 18 times square root of 5 pi squared. And then the lower bound, we have just pi squared, and when we square, we take t squared. So we have 2 root 5 pi squared, and so then subtracting, we end up with 16 pi squared times square root of 5. So there we go. There's our answer. Okay. So that doesn't much help us understand what we just calculated, but at least we know how to calculate these things. It's very simple. Again, you start off, you parameterize your curve, then you compute the length of the derivative, so you have your arc length element, and then you just plug everything in. X of t for x, y of t for y, z of t for z. And you use the corresponding pieces of your parameterization to replace x, y, and z's. And so in the end, you've gotten rid of all of your x's, y's, and z's, replace them with functions of t's. You've replaced ds with the length of r prime, which is a function of t, and you have a regular old definite integral. Now, what does this mean? Let me try to give well, probably what will be somewhat of a lousy sketch, and then we'll point you to other resources. So let's say that we have a function of 2 variables. Right? If we graph that, we end up with a surface. So here we go. We have this surface. Okay. Well, let's say down here in the plane, this is the xy plane down here, that we have a curve C. Okay. Well, this curve, you can extend it up, and let me see if I can do a little better job. it hits the surface at some point along everything along this curve. So we come straight up from this curve, and it hits various points on that surface, right? And so the image of that curve up on the surface is itself a curve up on the surface. And maybe we'll do this. Okay, so we have a curve on the surface up here, a curve down in the plane. So this is the image up here is the image of that curve up on the surface. Think about what does it mean to take a point on this curve and plug it into our function. Well, that's really kind of giving you a height, right? So you can think of that's like a height. And if you then consider what is ds, well, ds is like a little chunk of arc length. And so ds you can think of like, well, it's like it's a width. Okay? Well, if you multiply a height times a width, that very much sounds like an area, right? So what we're getting is a little strip of area. And so in the end, we add those up when we integrate. What we get is that this integral of, say, f of xy ds along c, where c is a curve in the plane, this is the area of a sheet. Okay? Well, net area, because I've drawn my picture as if z is never negative. But anyway, that can kind of start to give you an idea of what this thing is calculating. It shouldn't be too surprising, right? Definite integrals compute generally areas under curves or net areas under curves. And so this is still doing the same kind of thing, but it's the area under a curve drawn on a surface. So it's the area of again, kind of a flat sheet, but it's a sheet that can wander through 3 space. Now, the integral we just calculated above, that was for a function of 3 variables. That would be the area of the sheet beneath the hypersurface, w equals x squared plus y squared quantity times z, and above, if that even makes sense, the helix. So the problem with that geometric interpretation there is something that we really can't see because it operates in 4 dimensions. Let me mention finally that there is a example, my Maple example page, visualizing line integrals. I encourage you to go check that out if you want to see more visuals with this. And so there's an example of a curve being traced out on a paraboloid, and so we get that this line integral along a curve C there is calculating the area of that sheet. And anyway, so if you're interested, go check that out.